This is Geometry, Unit 8. We're working on the test review, starting with number 23. We're given some information about the circle. We need to write the standard equation of a circle. Recall that a standard equation is always x minus h squared plus y minus k squared equals r squared, where h and k are the center. So if the center is at 2, 4, you know that the 2 is the h and the 4 is the k. And we have a point on this circle. So that is our x, y. So in this case, we don't know what the radius is. So for us to calculate the radius, we're going to drop the negative 3 in for the x minus the h value. The y is 16 minus the k value. And we're trying to calculate what the radius is. Essentially, this is doing the distance formula from the center to the point on the side. If we were to make a real quick sketch of the center at 2, 4 and a point at negative 3, 16, we know that we would have a circle that looks something like that. So we're trying to find the equation of that circle. We don't know what the radius is. So that's what we're trying to calculate. So we get negative 5 squared plus 12 squared equals r squared. 25 plus 144. So we're looking at this and we get 169. So when we take the square root of 169, we get 13 for our radius. Well, we don't really need the full radius, do we? We just need r squared. So now we're ready to write the equation of our circle. We have x minus, the h value is a positive, so we write x minus a 2 squared plus y minus 4 squared equals r squared. So that's 13 squared. So that's 169. That's the equation of the circle that has a center at 2, 4 and another point that we know of at negative 3, 16. Here we have an earthquake, as we also have a seismograph that has readings for 3 different locations. We have one reading at 2, 1. Now notice the units here on our graph. They're going by 2's. So when we say 2, 1, 2 is 1 unit, and 1 would be half a unit up. Now we're supposed to go 5, a radius of 5. So 1, 2, 3, 4, 5. 2, 4, 5. So there's our circle. That means that this seismograph calculated that there was an earthquake within 5 miles of this station. Now we have another station at negative 2, negative 2, and it reads that there is an earthquake that is up to 6 miles away. So 2, 4, 6, 2, 4, 6, 2, 4, 6, 2, 4, 6. So now with this second spot, we know that the earthquake has to be either in this location. Wherever we have the centers, the earthquake was exactly 5 miles away. We just didn't know what direction it was. In this case, the earthquake was 6 miles away. We just don't know which direction it is. There's only 2 spots that fit that scenario. And it's looking like this one might be the magical answer, but we'll have to see. Now we're going to have a reading from -6, 2, 4, 6, +4. And it has a radius of 2. So that's where this is also hitting. So since this spot here was hit definitely by 2 of the spots, my circle just probably needed to be just a tad closer, and it would have hit right on top of it. It was a drawing error. So graph the 3 circles. We did that in one coordinate plane to represent the possible epicenter. That means the center of the earthquake, by determining the seismograph readings. What are the coordinates of the epicenter? Well, we found out that was -2, +4. That's where all 3 circles intersected. Could people feel the earthquake up to 9 miles from its epicenter? So, could people feel it 2, 4, 6, 8, 9? Could people feel it 9 miles away? And the answer is yes. It looks like they could go 9, 10, 11, even 12 away. 2, 4, 6, 8 away that direction. And 2, 4, 6, 8 away in that direction. People could feel the earthquake, or could people feel it up to 9 miles away? It looks like it was measured inside each one of those. And could a person feel it at 4, -12? Or, sorry, 4, -5. 2, 4. 2, 4, 5. And the answer is no. This is outside all of the circles. No one had reported feeling it outside the circles. So what we're going to look at here, we're going to try to determine if 9 is possible. I misread this question. This is people could feel the earthquake up to 9 miles away. So 9 miles away, they could feel it. The question is, how does 4, -5 work? I was reading it as inside the circles and outside the circles. That's incorrect. These offices, they're like buildings at each one of the centers. They measure how far away this epicenter happened. They just don't know which direction it happened. So when you have 2 offices doing measurements, we found 2 possible locations. Now we found a third office that where they all overlapped together was our epicenter. It's the only spot that all 3 offices found to be their correct distance away. Now the question is point 4, -5 going to land within 9 miles? So to test it, we say that r squared equals x minus a -2 squared plus y minus 4 squared. So 81 this is x plus 2 squared plus y minus 4 squared. Now what we need to do is plug in our x, y to see if these are going to equal each other. So 81 equals 4 plus 2 squared and negative 5 minus 4 squared. So 81 equals 6 squared and negative 9 squared. Does 81, is the question, equal 36 plus 81? Well, of course not. 81 does not equal 117. So no one can feel the quake, our earthquake, at 4, negative 5. We're looking for the circumference of our circle. This is a diameter. We know the diameter is 13. We have a circumference that equals pi times diameter, or diameter times pi. So we're going to say pi times 13, so we call that 13 pi. And if we were to convert that with our calculator, we should get 4084, and these are inches. Circumference is a distance, just like diameter is a distance. This time we're given the circumference. What is the radius? Our circumference, another formula we could use is called 2 pi r. If our circumference is 6598 and we're looking for 2 pi r, we're going to divide to get the r by itself. Remember, you may need to put parentheses around your denominator, and you'll get approximately 10.5 for your radius. Here we're looking for the area of the circle. We're given the total diameter is 24.8. The area formula is pi r squared. So to calculate the area, we plug, if that's our diameter, we're looking for radius. So we need half of our 24.8, which is going to be 12.4. So we plug our 12.4 in there to be squared. When you square 12.4, we get 153.76 times pi. That would be your exact answer for your area. Now we're going to multiply that together, and we're going to get 483.04. And those are centimeters squared because it's area. We're looking for the arc length. If the circle has a radius of 6 and a central angle of 60, not sure why the exclamation point's there. It's a conversion with reading what the special units of degree were. So arc length, we use our arc formula over circumference, which is 2 pi r, equals our angle over 360. So what we don't know is our arc length over 2 pi times 6 equals 60 over 360. So the arc length, we're going to cross multiply, is going to equal 12 pi times 60 divided by 360. And if you type that all in your calculator, you should come up with 6.28 centimeters. and that's the length. Now we're looking for the measure of arc AB. Recall that the measure of arc is a degree value. Whenever you're looking for the measure of an arc, the length of an arc, like we did over here, is the centimeters or inches or yards, meters, things like that. The measure of an arc is considered to be the same as the central angle, which are both in degrees. This 2388 is in our units, so that's the length. We're still going to use this arc length formula, and we have our 2 pi r. We're looking for the angle over 360. Our arc length is 2388. The radius is 12. We're looking for the angle over 360. So if we're looking for the angle, we need to get the angle by itself. So we're going to multiply the 360 up. Get 360 times 2388 divided by 24 pi. And you may need to put parentheses around that denominator. And that's going to give us this angle value. And the angle value is going to be 114.02 degrees. Here we're looking for the radius of our circle. Again, they give us the arc measurement. So arc GH over the circumference, which is 2 pi r, equals the angle over 360. That's the formula for calculating arc length. We can use it to find different parts: the arc length, the circumference, or the radius, the central angle. Well, of course, this is always 360. So we know we have 19.71 over our circumference. That's what we don't know. I'm going to use 2 pi r because we're looking for the radius. So that helps me remember that I got to solve all the way down to r. Our central angle is 55 over 360. Here we have to cross multiply both ways because our unknown is on the bottom of the fraction. So I need to multiply it up. So it's with the 55, 2 pi r, and I have to bring up the 360 to keep it away from the r. So 1971 times 360. Then I'll end up dividing to get the r by itself. I'm going to divide by the 55 and I'm going to divide by the 2 pi. You can do that all together. So when we multiply, we'll say 1971 times 360, that's this amount, divided by 55 and the 2 pi together. That's going to equal our r value. So our r value, try it with your calculator to be sure you know how to type it in, is going to be 2053, and that's going to be in the units of centimeters. You would need to put parentheses around the denominator if you type that into one big calculator problem, especially if you're using a graphing calculator. On the next page, we're going to find the area of the shaded region. So we see that the radius is 4. So we have a formula. It's very similar to our arc length formula. It's sector or sector area over the circle area, which we're going to find the area of the shaded region. So pi r squared. We're given the r, so we can calculate the area of the circle. We're looking for the area of the sector. The central angle over 360. So the sector area, we'll just write sector down, over pi r squared equals our angle, which is 65 over 360. So what it's saying is when you open up an angle to be 65, when your radius is 4, what's the area of your shaded region? We're going to cross multiply. We only need to go one way, because that's 65 times 16 pi over 360. So using our calculator, we'll see that the sector area is going to equal our two values down here, which is 9.08 inches squared, because this is an area of a circle. Next, we're going to use the same formula, but we're going to calculate for the area of H. We know what the sector area is. Sector over the area of the circle equals the angle over 360. The sector area is 2379. The area of the circle is unknown because we don't know the radius either. We're looking for an 80-degree angle over 360. When we're given this 80-degree angle, we have a sector value of 2379. We should be able to work backwards to figure out if 80 gives us 2379, what would the whole thing give you? That's the question. So we're going to cross multiply both ways and get 2379 times 360 equals 80 times A. So we're going to divide by 80. So 2379 times our 360 divided by 80 equals A. And that comes out to be 107.06. Those units are feet, and it's area, so it's squared. That's the area of the entire circle. Now this one, it's a little bit different. I know it has an exclamation point, but it doesn't mean that. It's just degrees. It's just the way the computer was converting that symbol. So we're looking for the diameter of the circle. Before we find the diameter, we need to come up with a radius. This is my plan. You got to come up with a plan to answer these questions. You don't just do the problem. You got to think about what it means. It's a little bit more than just following through with the equation, because the equation doesn't give you a diameter. But if I use the information that's given to me to find the radius, then I can use it to find the diameter. They're talking about area. The area of this sector is 3149. So I have a sector over pi r squared, because I'm looking for the radius, so then I can find the diameter. I know it's pi r squared and not 2 pi r because we're dealing with area. Over angle over 360. The sector is called EGF, arc EGF. Well, that's not true. Sorry. That's if we were naming the arc itself. We're not naming the arc. We're looking for the sector area. So let's just leave it with sector. Pi r squared. Now the angle. we have an angle here that's 51. If we were going to calculate the area of this shaded region, I need to know the area of this shaded region. So how do I figure out the area of the shaded region? Take 360, subtract the 51 to get 309. So my angle is 309. That tells me that I'm looking for a really big degree value. If I just use 51, then I was looking for a small degree value. So we're looking for the sector. Oh, sorry. Did it again. The sector's already been given to us. The sector area is 3147. And we'll cross multiply to get 3147 times 360 to equal 309 times pi r squared. I'm going to divide by the 309 and the pi. Let's just do it all together. And when you calculate that all together, we end up getting an r squared value of 11.67. r squared. You may need to use parentheses around your denominator. Then the radius is the square root of that value, which the radius comes out to be 3.42. So the diameter is going to be 2 times the radius. 2 times 3.42. So the diameter comes out to be 6.83. And those units are meters. Remember, that's a distance, so it's not squared. Okay, last two questions. This circle is broken up into 8 equal pieces. So we're going to take the total area because we're looking for the area of these shaded regions. So we need to figure out what is the area of one shaded region, and then we're going to multiply that by 3. All 8 sectors here would have the same area. We know that because all their arcs are the same. So we're going to start out with the sector area over the circle area, pi r squared, equals the angle over 360. The sector area over pi 13 squared equals our angle. Now, for us to figure out what the angle is, we're taking 360 and breaking that into 8 equal pieces. When we break that, we get 45. Now we're going to solve for the sector area. So the sector is going to equal 45 times 169 pi over 360. So this sector area is going to come up to be 66.36. And how many different sectors are we looking for? We're looking for 3 times 66.36. That comes out to be 199.09. Those are inches squared. Now, as I was working through this problem, there was actually another way. It's essentially the same problem, solving it the same way, but you could start out with just the area, which is pi r squared, which is 169 pi. Then we're going to cut 169 pi by 8, which would give us our 66.36. And then we have 3 of those. That would be another way to have calculated the same question. As I look over the rounding, this may round up to be 199.10. If you look at your calculator. Okay, last question. Here we have a big circle. The radius of this big circle is 9 plus the 3.5. That gives us a radius of 12.5. We also have a smaller circle in the middle with a radius of 9. What we're going to look for is area of the big circle minus area of the small circle. So we're going to take pi r squared minus pi r squared. Pi 12.5 squared minus pi 9 squared. So when we calculate this together, we get 490.86, and we subtract 254.46. That's that value to be 490, and that's that value to be 254. Subtract these two from each other, 236.40, and these are meters squared. One thing I wanted to point out is for question number 33 down here, we figured out that we had 6.83 meters, not 16. We had 6. So this answer key was a bit off. It had an extra 10 to it.